take-home quiz. It's I will email it to you guys this afternoon, hopefully early this afternoon, hopefully not too late. I'll have all the instructions on there for you guys, so we're not going to go get into that too much. But like I said before, everything's fair game, right? I just ask that you please don't, just try not to, just use your brain and then check your work. But everything's fair game. You can look through old videos and stuff like that. If you're like, oh man, I know we talked about this. Go find the video, look it up, right? But that should tell you that this is going to be more difficult than other quizzes that you've had, right? So, okay, the main event. I've been alluding to this for 2.5 years. Okay, this is the big thing. Now, sine and cosine are periodic, right? Meaning, like, you know what we mean, right? They repeat, right, over and over and over again. And interestingly, their derivatives are periodic. So, like, if for instance I say f is sine, I could have chosen cosine. The operation take derivative of is also periodic, right? Take the first derivative and we get cosine. Okay. Take the second derivative and we get negative sine. Take the third derivative and we get negative cosine. And then once we get to 4, the fourth derivative, we come back to where we started. So it's periodic, right? You take and you could even think about this as the 0th derivative of this thing, gives you whatever it is. And then you do first derivative, second derivative, third derivative, fourth derivative, and then if you keep going, take derivative of, you end up right back where you started, right? Or, well, here, you know what I'm saying, right? Eventually, and so this is also periodic. It's cyclic. Think back to Algebra 2. Was there something else that was cyclic or periodic? Can you think of anything? It would look a lot like this, where...
Oh, I, when you took the...
Good! So in other words, right, we know that I is just I. So I to the first power is I. But I to the second power is what?
-1.
So this operation was take derivative of. And when you start with sine, or cosine, you get this periodic thing. This is, okay, start with I, and the operation is multiply by itself. And so you take I and you multiply it by itself, and you get this. Now, do that again, multiply by itself again, and you get what? Negative I. Then we multiply by itself again, and we get 1.
Just 1, yeah.
Right? Because negative I times I is negative I squared. Negative I squared is negative 1, so 1. And that's the same thing as if we had it to the 0th power, because anything to the 0th power is just 1. Or, I mean, we could keep going and say, okay, do it again, and now you're just back to where you started. And either way, it doesn't matter where you start in this chain, because it's a chain, right? Multiply by I just has this cyclic nature. Interesting. I'm going to keep this up here. This will be helpful. This will be helpful for what we're going to do. And remember, when it goes to 5, we just come right back to where we started, right? So 6 would be here, right? So this is the same thing as I to the 5th. This is the same thing as I to the 6th. This is the same thing as I to the 7th. Same thing as I to the 8th, and so on, right? Yeah. Okay, everybody with me? Okay. Now, you remember yesterday or last time, we started off, I put 3 series up there, and I said, you better be able to recognize these series. I'm going to write one up here. This is pop quiz. This is a series for something. This should just be e to the x, right? So, okay, yes. Okay, good. Everybody wins the pop quiz. All right. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus Okay. And we'll cram one more in here. Okay, over 7 factorial, and it keeps going on and on forever and never stops. Okay. Now I could, remember, this is a function. I could plug anything in here for x, right? Like this is whatever goes in here. I can just plug something in, right?
Yes.
Right? Okay. So now I'm not sure how or why or whoever, I know who, but what the reasoning was to try what I'm about to do. But watch what happens when we do it. I'm going to plug in, instead of just plugging in an x, I'm going to plug in an I times x. I times x. Now let's just compute and see what happens. Let's just play with it and see what happens. Okay, so, okay, this is the same thing as just I times x. Now, I to the x squared is the same thing as I squared x squared, right?
Yes.
Right, because that's just ix times ix, and you could rearrange. And what's I squared? Well, let's just do it this way. So I'm going to go plus I squared x squared over 2 factorial. Now then the next one would be I cubed x cubed, 3 factorial. Then I to the 4th x to the 4th over 4 factorial. I to the 5th x to the 5th over 5 factorial. I to the 6th x to the 6th, 6 factorial. I to the 7th x to the 7th, 7 factorial. I to the 8th x to the 8th, 8 factorial, and so on. Now we have our handy dandy cheat sheet right here. Let's go ahead and see what happens, right? Maybe we'll make our lives easier. We'll see. I to the ix is just ix. Okay. I squared is what?
Negative.
Okay, so that's the same thing as negative x squared over 2 factorial. What's I cubed?
Negative I.
Negative I. So I'm going to write that as negative I times x cubed over 3 factorial. Is that good? Can I pull him out of the top and just treat him as a constant? Okay, that's how I'm used to writing. I just want to do that. Now I to the 4th is just plus x to the 4. Okay. I to the 5th.
Just I.
Yeah, nice cheat sheet right there, right? So plus I x to the 5th over 5 factorial. I to the 6th.
Negative 1.
Negative 1, so that's the same as minus x to the 6th over 6 factorial. I to the 7th?
Negative.
Negative I x to the 7th over 7 factorial. I to the 8th is just 1, so that's plus x to the 8th over 8 factorial, and so on. Maybe let's, so there's obviously a complex number. Right, you plug in a complex number. The complex numbers we usually write as you have your real part plus I times your imaginary part, right? Or I times this. These are real numbers here, right? And we usually just group them together. So, like for instance, if I said, okay, write this: 5 plus 2I minus 7 plus 9I. Write that as a complex number, I would just, that means just group the real parts together. So you have minus 2 plus 9, 10, 11, so I times 11, right? That's how you would do that. Let's do that here. Let's just group all of the real parts together and all of the imaginary parts together here. So, okay, the reals go 1 minus x squared over 2 factorial. Plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, and so on. Now we have all the i's. So we have plus ix minus ix cubed over 3 factorial plus I x to the 5th over 5 factorial minus I x to the 7th over 7 factorial, and so on. And each one of those has exactly one I in it.
Yeah.
So I could factor out an I, and let's see what I get. I get, over here I have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th, and so on. Now, pulling out an I get x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x 7 factorial. What's that?
Sine of x.
It's what?
Sine of x. Cosine.
Cosine.
Oh, yeah, cosine.
Even, right? And that's one of the interesting, we know that cosine's an even function. That is, right? Cosine of a negative x is the same thing as cosine x, right?
Yeah.
And yeah, that's an even function. You plug in a negative x, they all go away because it's all even powers. And so yeah, that's one way you could, if you can't remember which one's which. And the odd one, sine, has the property that it's an odd function, right? Yeah? Right? We all remember that? And you can kind of see it, that's the case. Plug in a negative number, those will all be negative, and you can factor out a negative. Interesting. Okay, so back to here. So this is cosine
Plus I times
plus I times
sine.
sine x. Therefore, e to the I times x is equal to cosine x plus I sine x. This is called Euler's formula. You guys know who Richard Feynman is? You ever heard of Richard Feynman? He's a physicist, like wicked smart. I mean, it's almost a tautology, a smart physicist. Yeah, no, but like revolutionized a bunch of stuff. He called this the most remarkable formula in mathematics. And yeah, but we're not done. We're not done. So I'm going to rewrite. So there's the proof. That's the proof.
Yeah.
Euler figured this out. And I remember asking my calculus teacher, like, why? What was his reasoning for trying this, right? They didn't write like that, like in his papers he didn't say like, well, I had this idea and such and such. So my teacher's answer was, he's a genius. Just like, So, and you can imagine, right, like when you look at e to the x, and like I had it written up on the board, like this, 1 plus x plus, when you came in last time, right? And then below it you could put cosine x, and you get 1 minus x squared over 2 plus x to the 4th over 4. And if you write sine, you could write that as there minus x cubed over 3 plus x to the 5th over 5. It may very well have been that he's like, dude, come on. Those have to be related, right? There's gotta be a way of doing this. And maybe he had in his head like, well, hold up. We need something that goes positive, positive, negative, negative, right? Positive, positive, negative, negative. To line these up. Is there something I could plug into there that goes positive, positive, negative, negative? And of course he's a super genius, so he's like, well, hold up, this goes positive, positive, negative, negative. Maybe, I don't know. Nobody knows. Maybe somebody knows, I don't know. But you could kind of reason like there's some kind of connection there, maybe what happens, but we've seen it. Like we just proved it. Plug in an ix and that's what happens. Interesting. So I'm going to rewrite this up at the top. Euler's formula. That is e to the I times, and you can see this with a theta. If I plugged in a theta, in fact, let's just go ahead and do that. E to the I theta is cosine theta plus I times sine theta. Okay, so that's Euler's formula. And from that, my friends, we can get the most beautiful result in all of mathematics. what happens when I let theta equal pi? So I'm just going to plug it in. E to the I times pi must be the same thing. We've just seen it as this right here. Okay. What's cosine of pi?
0, 2. No, -1.
Good. -1. What's sine of pi?
0.
So I times 0 is just 0. E to the I pi plus 1 is equal to 0. This is called Euler's identity. Identity. Now we're going to take a minute here. So, this right here, it's widely known as the most beautiful and or famous theorem in all of mathematics. This is, I looked this up yesterday. This guy, Benjamin Pierce, he was a 19th century Harvard professor. In a lecture, he proved this, just like I did. And he said, this is absolutely paradoxical. We can't understand it. We don't know what it means, but we've proved it. Therefore, we know it must be the truth. Check this out. Now, not all. I mean, it looks cool, right? I'm like, whoa, hold up, but yeah, let's kind of look. Let's look at this a little bit more. E to the I pi plus 1 is equal to 0. Euler's identity. Okay, so let's look at what we got here. First thing to notice, there's 0, which is the additive identity. There's 1, which is the multiplicative identity. There's E, which, well, that's Euler's number, right? And it's not just Euler's number. Like, it's everywhere, right? Like, you should have seen this by now. Like, with differential equations, your solution is of this form, right? Like, yeah. Like, it's, and like I said, differential equations are like how are how nature and math interface, right? It has pi, the circle constant. And it has I, the imaginary unit. So it relates these 5 fundamental constants together. I remember when I brought up E, when I first taught about E, somebody in class would, I said E it's a constant, it's irrational, it's like pi, right? It's a transcendental number, it's like pi. And somebody said something about pi, and I was like, oh, they're related. They are related somehow. We're not going to get there yet. This is how they're related, right? Not only that, right? So this gives a relationship between the additive identity, the multiplicative identity, Euler's number, the pi, the constant of a circle, right? And the imaginary unit. And check this out. This is really cool. Because every one of the basic arithmetic operations shows up exactly once. Addition shows up exactly once. Multiplication shows up exactly once. I times pi. Exponentiation shows up exactly once. Right? So those are the basic operations of arithmetic, without which, like, nothing else, like the very most fundamental things that you learn, that are right there. And equality is there too. Right? The most beautiful result in mathematics, right there on the board, and we just proved it. All in one statement, all in one compact little statement. If you want to get a tattoo. Anyway, all right, so there it is. I've been waiting for this for a long time. Now, check this out. We're not done. We're about to bring a lot of stuff together right now. So, yeah, we'll get done. Okay, all right, so there's that. oftentimes, like if you're watching a movie or a show or something, and they often do this thing where like they'll zoom in on somebody when they're thinking, and a bunch of like equations will like fly by their face, you know. The e to the I pi plus 1 equals 0 is one that you'll often see going by. It's, yeah. Okay. Okay, so, how do you parameterize a circle?
Oh, so,
And let's say the unit circle. So what I want, right, I want a function, I want two functions, x of t, y of t, so that you give me a t and it gives me a point here in the unit circle. You guys remember?
Oh, it's like cos.
Uh-huh.
Sine?
yeah.
Uh-huh. Uh-huh. And that should parameterize the unit circle. Why? Well, I don't want to just try to recall this from memory. Let's think about this. Unit circle, that means that radius is 1, right? We're looking for an x value and a y value right there. And we're going to imagine that that's the angle t. Then what we have here is a big fat 1. This length right there would be x, right? This length right there, that height would be y. And so, if that angle is t, if you go cosine t equals what over what?
X over 1.
X over 1, right? Sine of t is
Y over
y over 1. And so yeah, indeed, the x value that you're looking for at any time t would be cosine. The y value that you're looking for at any time t would be sine. That's how you parameterize the unit circle, right? Right?
Mm-hmm.
Right? Okay, so we all remember this. Now, what if instead of talking about vectors, we were on the complex plane? So this point, x comma y, we would write it as x plus I times y, right? And so, how would I write this in terms of complex, in terms of a complex
Cosine plus
cosine, cosine t plus
I times
I times sine t. This thing is the unit circle. E to the I theta, for a theta going between 0 to 2 pi, is the unit circle. That's pretty cool. How do you like that? Right? And just remember this, all this I does when you're talking about where you are in the complex plane, this is just a way of giving you your x location and your y location, right?
Yeah.
Like that's all that is. Because you have your, in any complex number z, you just have your real part, and then you have I times your imaginary part. And really that's just an x coordinate and a y coordinate. This is just a nifty way of writing it. Like these functionally are exactly the same thing. The only thing that you're missing over here is you can't just take two vectors and multiply them together and get a new vector. You can, but it's not. It's different. This is exactly the same thing as this. It's just a different way of writing your vector. When you bring this in, now we have rules for how you multiply complex numbers together, right? First outer inner last, and then the I squared becomes a -1, blah, 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 right? But ultimately, this is, you could, if you have a point on the plane, x, y, you could write it as a vector, or you could write it as a complex number. And that's what that would look like. That's the unit circle. Now,
So if you graphed e to the I times theta on a complex plane, it would just be a circle.
yep. And you tell theta to go between here and here, then it would do that. If you told theta to go between there and pi, it would give you the top half. If you told theta to go between -pi and pi,
It would still be.
it would still be, it would start here, go around, and come back. And so that's like, and because this is periodic, right? It keeps going around and around. Just like we've always talked about with the unit circle, right? Okay, all right. Okay. How do we parameterize a circle of radius r? So now, here we go. Same question, but now we want r. You guys remember what you do? Because there's a couple different ways we can think about this.
R times cosine of x,
Mm-hmm.
and then comma r times sine of x.
Yes, and so let's think of why that's the case. So on one hand, right, you have your r here, you have your y there, your x there, and you have your t. There's no x, right? you said cosine of x, but you're talking about t. You could say, okay, cosine t is x over r, therefore r cosine t is x. Ditto, you get your r sine t is y. You could do it that way, right? And so, okay, so we're parameterizing this guy. This would be r cosine t, r sine t, like that. Okay. Okay, or you could think about it as, okay, you have some big old r right here. Here's your circle of radius r. What you could do is say, where is this guy on the unit circle? Right?
Okay.
T. And right here is your cosine t. Right here is your sine t. And since you want to stretch your radius from 1 out to r, just multiply every length, every side of the triangle, right? 1, y, x. Just multiply everybody by r, and everybody stays the same, right?
Yeah.
So then this coordinate here would be r cosine theta. This coordinate here would be r sine theta. So a few different ways of thinking about it, right? You could like find the triangle and get that, or you could say, well, wherever you are out here, we could find where you would be on a smaller triangle, and then stretch it out. Or conversely, if you're going the opposite way, you divide it by whatever to get your new r, right? Anybody inside the unit circle, you could say, okay, well here you are, if it's 1, divide by whatever it would be to give you your new r, and etc. Right? Okay, okay, okay. Okay. So that's how you parameterize a circle of radius r. What would that be in complex numbers? How could I write this as a how would I write this point if we know that that point is at r cos, r sine? How would you write that as a complex number?
R cosine
R cosine t
plus
I times
r sine.
r sine t. And so, oh, it looks like I could factor out an r. Oh, so that's r times e to the it, or theta if you like.
So
Oh,
any
wait a second. What were you gonna say? What were you gonna say?
so any circle. Wait. If you know the radius of the circle, you just plug it in and do that.
Well, hold up. Because let's think about this. You give me any point on the complex plane. A plus I times B. It has some location here, A. It has some location here, B. Now remember, for a while now, I said there's 2 ways I could tell you how to get from here to here. I could tell you, you go A blocks to the east, and then B blocks to the north, and that's how you get there. And its coordinates would be A plus IB. Or, I could tell you, you know what? Shoot an angle of whatever this is, call it T, and walk a distance of R units. And how would you get there? Well, this is where that point would be, right? I mean, we just did that. right? We went and derived that and found whatever t happens to be, you would do this, you would do that, and blah, 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 blah. And that's where it would be on the plane. So in other words, every complex number can be written in this form. That is, every complex number can be written in this form right here. And that is polar coordinates. Up until now, we've been saying write your polar coordinates as r theta. Well, that's not how you do it. You do it like this, r times e to the I theta. Because that's what it is, right? Right? Now, here, here's an example. So I really want to drive this point home. So, polar coordinates even, right? Like, it all comes down to that. So, let's say, so first off, forget everything I just said. Easy, right? So, let's just say, I told you to find the polar coordinates of the point √3 plus I. So here's some complex number. Let's call it z. √3 plus I. And you want to find the polar coordinates. So we need two things. So first off, we know that this length is what?
√3.
That's √3. And this length is what? 1, because that's I. And so now we have a triangle, and it's 1, right? So we have our triangle like this. It's 1, it's √3 there.
2.
And so what's the, yeah, there you go, right? And you should remember that. Or, I mean, if you really had no clue, you could say, well, √3 squared plus 1 squared is equal to c squared. That's the same thing as 4 equals c squared. So c right here would be 2. Okay, and what angle would that be right there?
Pi over 6.
Pi over 6. Right, because that's the 30, 60, 90 triangle. 30 degrees or pi over 6. 60 degrees or pi over 3, right? Okay, so what is this in polar coordinates? So now let's just forget everything I just did. R theta would be what?
2, pi over 6.
2, pi over 6. Now, what I've just said is that
So it would be 2.
this number, just check it out, what I just said is that this number, √3 plus I, is the same thing as this, which we're going to write in the form r e to the I theta. So r e to the I theta. We just need to find r and theta, which we already did. We just found r and theta, so let's plug it in. R is what?
2.
And theta is
Pi over 6.
pi over 6. Now, let's use Euler's formula. What is the, look up there, and you tell me what to write right here.
Cosine of pi over 6 plus I times sine of pi over 6.
I'll give you a cheat sheet here. Pi over 6, 1, 2, √3. What is cosine of pi over 6?
√3 over 2.
√3 over 2 plus I times, what's sine pi over 6? Multiply him back in, and what do we get?
√3 plus I.
Oh man. It's the same thing, right? How cool is that? Every complex number has this form right here. And it happens, like up until now, we've been saying stuff like, and it's kind of like you can't really add these together. It's just, this is just another way of doing it. It's like, no, they're exactly the same thing. It's just a different way of writing it. And they are exactly the same thing. That's really cool. So, every point in the complex plane has this form for some r and some theta. Okay? And yes, just like it was when we first did polar coordinates, 0 is a funky one because that theta is not unique. If the origin, 0, right? Well, r e to the I theta, well, r is obviously 0, and so then theta could be anything. It kind of makes everything break down. 0 always makes everything break down. But anyway, okay. So now check this out. Think back to Algebra 2. And I said, you give me any two complex numbers. How do I want to write this? Z. And let's say W. And when we multiply them together, there was this nifty little rule.
You multiply
You multiply what's?
the real number.
It's called something.
I don't remember. Wait, what was it called? No.
It's called the modulus.
Oh yeah.
You multiply the moduli, which is the magnitude, which is the distance from the origin. And then what was the rule? The other rule?
You add the angle.
Yeah, it was called the argument,
Yeah.
Right.
which is the angle from the positive x-axis. Right? Okay, all right. So then, okay, that's the rule for that. So in other words, since every complex number can be written in this form, there is some r and some theta for whatever z is, right? So z is over here. There's my number z. And he has some r and some theta.
Yeah.
Now let's say there's another point, some complex point. Let's put him up here, W. And he has also some, let's not call it an R, let's call it an S. Some distance away, S. And some angle, let's call it phi. We said that when you multiply z times w, well, okay, let's just do that. We have z, which is r e to the I theta. W is s e to the I phi. Let's see, we could rearrange this and say that's just a number times a number times a number times a number, so I could do it in this order. R times s times e to the I theta times e to the I phi. That's the same thing as r times s. We multiply the
E to
module.
the I theta plus I.
E to the I theta plus I phi, which is the same thing as e to the I times theta plus phi. And so the rule, which I just said, it's a rule, trust me on this, now we've proved the rule. Okay? Every point on the complex plane can be written in this form. And if you wanted to multiply them together, all you got to do is find their lengths, multiply them together, and that gives you the length of the new thing. And then add the arguments together. Well, that's why. Because this, just by virtue of being in the form that it's in, this is in the form rs, let's call it t e to the I alpha. That means there's some angle, alpha, and there. Well, that defines some point on the complex plane. And so now to really drive this home here, let's say that z was that first one we were looking at, root 3 plus I, yeah. Now let's do another one. How about 1 and root 3I? So w is 1 plus I times root 3, right there. Now, what's w in polar coordinates? We already found, and we found that this was 2e to the I pi over 6. Yeah?
W is S phi.
Yeah.
So
Right.
S times
And so what are s and phi?
S,
So here you go.
1 times
So 1
e to the I.
root 3i. So that means that length is, what's this length?
Root 3 through I.
Root 3. Just the length. I don't care about the
Oh,
I.
right.
And what's that length?
1.
1. And so what angle is this?
Pi over.
Uh-huh. Here's your cheat sheet, right? 1 root 3, that must be a 2. That would be your pi over 6. That would be your pi over 3 right there. Okay. All right. And so, in polar coordinates, this is what? What's the length? Yeah. And what is that length?
So 2 times
2 times
e to the I times pi over 3.
I pi over 3. There we go. That's polar coordinates, right? Like, if I gave you this last year and said, find r theta, that's what you do. You go, well, it's 2. So 2. And theta would have to be pi over 3, and that's what you do. Well, now we know how to write it. And we're going to do a couple things now. We're going to verify that that's true. We already verified it with that. We've already done z, so let's do w. 2e to the I pi over 3 is the same thing as 2e to the... Oh, I'm sorry. That's 2... What do I write here? What?
Cosine.
Cosine of...
Over 3.
3 plus I times sine pi over 3.
I times sine pi over 3. What's cosine pi over 3?
1 over 2.
1 over 2 plus I times
Root 3 over
root 3 over 2,
And then
which is...
1 plus I root 3.
Okay, so it works. Okay, now we want to multiply them together. One way of doing this is to say, well, ZW is 2e to the I pi over 6 times 2e to the I pi over 3. 2 times 2 is 4. E to the I times what?
Pi over 2. Or
3.
I think it's pi over 2. Let's just double check, okay?
Yeah,
Pi over
3
6
pi over
plus pi over 3 is the same thing as 2 pi over 6's, yeah?
Yeah.
3 pi
So
over
that's 3 pi over 6, which is
Pi over 2.
pi over 2. So, that's the same thing as 4e to the I pi over 2. And what's e to the I pi over 2?
cos of
Okay,
Yes.
do it.
Cosine
4 times cosine
cosine
of
of pi over 2.
Cosine pi
plus
over
I
2
sine.
plus I sine pi over 2.
Cosine pi over 2 is 1.
Cosine of pi over 2 is what?
Is 0.
Wait, sorry. Yeah, 0. I was just thinking.
Yeah, I know what you're thinking. Alright, then
Plus
I
I times 1.
1.
1. So, what's 0 plus I?
I. 4i.
Or I. And indeed, if you just did the rule and said, well, you have some complex number, and it's 2 and 2. Multiply moduli, so it would be 4. And add the arguments, so pi over 3, pi over 6 is pi over 2. Pi over 2 lives right here, right? And it would stretch out to 4, so you'd be up at 4 right there, so that would be the point 4i. That's the point 4i. Now let's just multiply them together and see what we get. This is why this works. This is why. Because it's just a fact of nature. It's a fact of, yes, it's beyond, I mean, it's just crazy. It's crazy that this works. So z times w is root 3 plus I times 1 plus I times root 3. First, outer, and last. First gives me,
Root 3.
outer gives me
I
3.
3i
3i
Plus I.
So
plus I
Plus I
minus
squared.
root 3.
plus I squared
Root 3.
root 3, which is...
Root 3 plus 4i minus root 3.
Or just 4i.
Yeah.
Ha! Nice. So that's what all that mystery was about. And I planted that seed like 2.5 years ago because I was like, oh man, this would be so worth it if we put and because like if you're gonna do trig, it lends itself to that too. That's right there. Euler's formula, the unit circle. That's Euler's formula is the unit circle. Okay. Some time ago, I said this. Okay, ready? Okay, e to the ix is equal to what?
Cosine of x.
Cosine x plus
I
I sine x. Now, if I made this negative, that would be the same thing as e to the I times negative x, which would make this what?
Cosine of x minus.
Good, you jumped to the chase. But the idea, I'm saying let's just do it one step at a time. Negative x in here, right? Negative x in there. Cosine's an odd function. So cosine of negative x, I'm sorry, it's an even function. Cosine of negative x is the same thing as cosine of x, yeah? Sine of negative x is the same thing as negative sine of positive x, right? So take that and multiply it by I. How about let's just write it like this? I sine x.
Yeah.
Right? Everybody buy that? Right? So e to the minus ix is cosine. Check this out. This is kind of cool. So if you're going in the negative direction, so you're on a circle, you're on the unit circle. If you go in the positive direction, x radians, you're going in this direction, yeah?
Yeah.
If you are going in the negative direction, negative x, you're going in the opposite direction. And indeed, whatever value this turns out to be, cosine, so let's just call it, let's call it a plus I times b. Well, you're at the same a down here, right?
Yeah.
If you've gone the same number of radians.
Yeah.
So you're at the same a. The only difference is thanks to the circle being symmetric, instead of being at positive IB, you're going to be at negative IB.
Yeah.
Right? So that's what this is saying, like that is the complex conjugate of that guy.
Yeah.
Right there, right? Okay, here we go. Check this out. So one thing to notice then, if you have those two numbers, a plus IB and a minus IB, what happens if you add those two numbers together?
Just get
It's just
a. 2a.
You
Or
get
2A.
2a, right? So in other words, the imaginary part cancels out.
Yeah.
So if I add these two numbers together, let's see what happens. So on the left-hand side, what do I have?
E to the ix.
Right. Plus,
Plus.
minus I.
Minus ix. And what do we have over here?
Just
Cosine
two
of x.
cosines.
2 cosine of x's. And so in other words, you're telling me that cosine of x is equal to e to the ix plus e to the minus ix over 2. What was hyperbolic cosine of x? How did we define hyperbolic cosine?
It was. Yeah.
Wait, that's kind of cool.
So what?
Yeah, and you know, like when we did this, you know, it was like, oh, those power series look very similar. It's not just the power series that looks similar, right?
Yeah.
It's not just the power series. It's like the very form of it itself is that.
Oh, because it's.
And now check this out. Cosine is just e in disguise. Cosine is e.
It would be-
It's an exponential function.
Oh. Yeah.
Look at that. Like if I said, hey, here's this thing, and it looks like this. What kind of function is that? Exponential. Yeah, it's an exponential function. Cosine's an exponential function. And like I've said a bunch of times, like almost all the functions that you know about, they're really just e in disguise, right? Like you can get a lot of, like this obviously is e to the log ax, right, which is e x log a. So it's like obviously every exponential function of some base can be written as that, yeah. But cosine can be written in terms of e to the x. Not just cosine, because check this out. Watch what happens. So, back to our picture. You go up x, you go down by x,
Yeah.
and down by negative x, and yeah, if you add them together, that part goes away. What happens if you subtract them from one another?
Then the real part goes away.
And
The real part goes away. So one second. We just found that cosine x is equal to e to the ix plus e to the minus ix over 2. Now, instead of adding, we're going to subtract. So over here I get what?
E to the ix minus e to the negative ix equals
go on.
I sine of x plus I sine of x.
Which is how
Two-
many?
two
2i sine x's. And that kind of makes sense because if coming back to what we just said, if you have this number a plus ib, and you have this number who's just below it, a minus ib, if you subtract them, the real parts go away, right?
Yeah.
Whatever number that is, if you subtract them from each other, that part goes away, and now you've pretty much what you have left is double whatever b is, right? That's whatever that happens to be. It's because you were subtracting it off. Now you've subtracted something that's subtracted off. You've just added it to it, but now it's on the imaginary line. Well, so in other words, whenever you do this, you get an imaginary number. So if we divide by that imaginary number, now you just have a length. And so here you go, e to the ix minus e to the minus ix over 2i. This sine x. Sine, it is also an exponential function.
Yeah.
That's, yeah. Wow, how crazy is that? And like, back to that one quote, nobody knows what this means. It's so crazy. It's like, what is that? Yeah, but what does that mean? I don't know, man.
Yeah.
It's kind of crazy though. And like, think about how we introduced the exponential function at the very beginning, right? When we first did it, we got it from like compound interest.
Oh
And
yeah.
it was like 0.02 over some number of compoundings and
yeah.
stuff like that. That's one way of
5%.
getting there, right? And then it turns out that there's this cool, if you take a limit of this, right, you get some number, some weird number, and it has some cool properties. And then you take calculus and you're like, that actually, that's the function, that's its own derivative, that seems cool, and it's just there. And then it's like, yeah, and they're all related to each other. It's just crazy stuff, man. What does it mean? I don't know. Ask God when you get a chance. Like, what is this about? Why'd you do this? What are you saying with this? Okay, so in your homework, I'm sorry, in the what?
The quiz?
The quiz, thank you. In the quiz, I'm gonna tell you first to derive these things. Okay, derive them. In other words, start with Euler's formula and derive these. You do what we just did, right? Then I'm going to tell you to prove that the derivative of this one is this one, using just this. Okay? It's simple. And you think, whoa, what do I do with I? Well, okay, what's the derivative of this function?
K times
K times e to the kx. Yep. I is a constant. It's imaginary, but it's a constant. It's just a constant. There's nothing crazy about that. One thing, I might even put this on the quiz for you, because this I, negative I, is the same thing as 1 over I. Oops, wait.
Wait, negative. Oh, because it's. Wait, what?
Negative I is the same thing as 1 divided by I.
'Cause it's a one.
It is.
Oh,
But,
because
and so now here's one way you could do
multiply
this.
Top and bottom by.
Yeah, that's one way you could do it. You can multiply the top and the bottom like that, and you get negative 1 over I, which is just negative I. Another way you could think about it is to say, well, hold up, wait. I is a location on the unit circle. And so if I go up, right, okay, so this is e to the I pi over 2 right there.
Yeah.
If I go this way, that's e to the I minus pi over 2, right?
Yeah.
And isn't this the same thing as e to the I pi over 2 to the negative 1?
Yes, yes.
Yeah.
Oh, which is just 1 over.
And so that's just I raised to the negative 1.
Yeah.
Oh. 1 over I. And you see, this is what's going to mess you up, because you're going to go from 1 and try to show that it's this, but that minus I down there, you could rewrite it so that it's a minus I up in the top.
Yeah. Okay.
So just, you have all weekend to do this.
Yeah.
So I've given you way more info than you need. Now, okay, finally, one last thing I want to do with this. And really, we've talked about it before. It was in Algebra 2, we talked about it. But that was just, I was like, well, you just apply this rule. A negative times a negative is a positive. Okay, give me a negative number. Let's say negative 2. Negative 2 lives on the complex plane, therefore he has a polar representation.
Yes.
What's its radius?
Negative 2. Or 2.
Positive 2. What's its angle?
3 pi over 2. Oh, no, pi.
Aha, there you go. There you go.
Yeah.
Its angle, its argument is pi. So we could write this as that right there. Yeah?
Yeah. And e to the I pi is...
And so let's take another negative number. Let's say negative 3. It has, so this is minus 2. So minus 3, its length is,
3.
and its angle I pi. So when you multiply these two numbers together, negative 2 times negative 3, it's the same thing as multiplying this. What's 2 times 3? So I added it. Let me just write it out. Okay, so what's 2 times 3?
6 times e to the 2i.
And what's e to the I 2 pi?
It's just 0. 2 pi is 2 pi.
It's the same thing as e to the I to the 0.
Cosine of...
Yeah, let's just do it, right? Cosine 2 pi plus I times sine 2 pi.
So 1 plus 0. So 6 times 1 is just 6.
That's why a negative times a negative is equal to a positive. There you go. And yeah, and so this gives us a concrete way to prove that yes, indeed, any two numbers on the complex plane, when you multiply them together, it has the same effect as moving them around the complex plane. By how much? Well, it depends where they are. If they're here and here, then it's the same thing as adding these two angles together, and you get whatever angle pops out of that. That's where he ends up. The distance has something to do with the two distances that those are. Now, another way of thinking about this, right? Like from now on, that last step, I actually plugged in 2 pi into each one of these. Another way of thinking about this is if you know that e to the I theta is just a point on the unit circle, you could just say, well, I know what the unit circle does. And by this point, you should know a lot of points on the unit circle. So I could say, well, if theta is pi over 4, then I know that we're here. Pi over 4, so that should be at the point 1 over root 2 plus I times 1 over root 2. That's got to be e to the I pi over 4. Similarly, if I'm down here and this angle is pi over 6, we could say that's the same thing as e to the minus I pi over 6, or you could say it's the same thing as I 11 pi over 6, right? And it's just, you know where that is on the unit circle. You're like, oh, wait a minute, hold up, I know this. This is, that length has to be, so normally it would be a 1, 2, root 3, but I need to divide everybody by 2.
Yeah.
And so then this must be root 3 over 2 plus I times minus 1/2, so minus that guy right there. Because you know the points on the unit circle. And so this is the same thing as just the coordinate, the polar coordinates of the things on the unit circle. And so, I mean, if you want, yes, plug it in. And when I'm probably going to give you one that I'm going to say verify using Euler's formula, actually plug it in. But like for the rest of your life, you should just be able to think about this as synonymous with, it's a point on the unit circle. Where? Well, theta radians.
Yeah.
Oh, I said finally, but that wasn't final. There's one more thing to say. When we first started trig, and this probably would have been better. This has nothing really to do with Euler's formula. But, okay, when we first started trig, now let me get some of these out, folks. Okay, when we first started trig, we introduced, for the first time in your life, the idea of radians.
Yeah.
And it was like, and I made an argument as to why they're natural in a sense. I said, you know, because like you want to measure this thing, how are you going to chop up a circle? 360 is arbitrary. Not really arbitrary, because it's what do we call a highly composite number? Remember that?
Yeah.
Right? It has a lot of divisors, right? Like
More than any number.
more than any number below it. Like 12 is a highly composite number because it could be divided by 6, it could be divided by 4, it could be divided by 3, and it could be divided by 2. It has a lot of divisors, right? Same thing with 360. So it's not 100% arbitrary. It's not like they just threw a dart at a wall full of numbers. I don't know. It's like there's some reasoning behind it, but it's not. And I said it's not natural, in a sense. And my argument was kind of like, well, since we're talking about a circle, really, it makes sense to use the only real defining property of a circle, which is its radius, to define how far we go around it. And so then 1 radian would take you to here. 2 radians would take you to up there somewhere. 3 radians would take you to here. Pi radians happens to take you to there. But it's all defined by the radian. And I said it's a good way of, so it makes sense that we want to use the circle itself to divide, the only property of the circle itself to divide it up. Okay. That was bull. I just made that up. I didn't make it. It's true. It's true. There's something to it. But more to the point. What did we use to derive this formula?
We just took derivatives.
We just took derivatives. And so, what did we use? The only real thing we used was, let's see, sine of x plus h minus sine x over h. We used the fact that sine and cosine, we used the angle formulas, right? Or the, what are they called? The addition formulas, right? So we use that. Did that have anything to do with radians? No. Okay, no. We ended up with 2 limits.
Yeah.
And 1 minus cosine. Does that have anything to do with radians?
No, it works with degrees.
No. So, okay, so right. It would also work with degrees, right? Because we were taking the limit as it goes to 0, right? So there's nothing, we never said, okay, make sure we're in radians here. Everything we did works whether it's in radians or degrees, right?
Yeah.
And then we did some calculus and found these are indeed these. These mean the same thing. We haven't proven that yet, but it's true, okay?
It gives you it in radian, like.
What, I'm sorry?
Like when you graph it, it's how you would graph it in radians.
Here's the thing. This is what I'm getting at.
Oh.
If you plug in a 180 into here, if you just say, let's maybe it's in degrees, and you plug in a 180, you're not going to get 0. But if you plug in a pi, you'll get 0. If you plug in a pi over 2 into here, right? And of course, how do you plug in a pi? So this is what I'm saying, is like, if you do this, right, and you tell your computer 3.141592653, you take that number and you plug it into here, and you do that out to, I don't know, let's say the 71st one right here, 71 factorial. You take that number and you plug it in, you are going to get something very, 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 very close to 0, because, and then we would have to conclude that sine of pi must be 0. If you tried it with 180, it ain't going to work.
It would give you how much?
Yeah, it'd be massive.
Well, no, it wouldn't.
Oh no, because it's.
It wouldn't. And if you go far
Okay.
enough. If you chopped it off here, yeah, it's probably going to blow up. But if, I mean, well, actually 71 is probably good enough.
Yeah.
Because I'm willing to bet that 180 to the 71 is much, much, much small. Actually, no. You'd probably have to go out past 180. So if you went to the, how about 301? Oops. You do this. You go all the way out to there.
Yeah.
This is going to be way bigger than that, I think.
Yeah, that makes sense.
Right? And so, which we'll prove that eventually. We'll prove that eventually this setup, the factorial wins. But this is the cool thing. We never specified radians. But this thing, which seems to somehow be fundamental, written into the fabric of the universe, somehow, by someone, some mind, apparently, it's in radians. It's just in radians. Like, if you graph this, you just go to graph this thing, it, of course, the top one's going to look like this. And if you look right here, this does not happen when you plug in a 90. It happens when you plug in a number that's really, really, really close to pi over 2. So somehow, this is what I meant when I said it in trig class. It's natural. It's somehow very natural. It is the right way of doing it. For reasons we don't really know. But like, I mean, how does it? And so I made an argument like, it makes sense that you measure a circle with its radius, and if you're chopping up a circle, that's how you do it. But it's much deeper than that. It just happens to be the case that radians are the thing that make it do the thing that you expect. Yeah. Crazy. So that's all I got for today. I hope you guys enjoyed it.